one node having a rumor, and it had to reach the whole population. And this time we are going to look at a different model. So each node has its own value or opinion or belief. And then all the nodes have to agree on a common value. So we are going to look at some models for that. As last time, the individuals who we also call agents, these are represented by the nodes of a network. And then each node has a value associated with it, which may be the opinion or preference or belief of that agent. And then these agents or nodes are going to interact according to some specified rules, which could be random. And based on this interaction, they will modify their values. And then this gives rise to some dynamical system, and we want to understand the long-term behavior of this dynamical system. So we want to know particularly if all the values of the different nodes either get closer to each other or maybe even reach exactly the same value across the whole network. Does this happen? And if it happens, then how long does it take for that to happen? So these are the two questions we are going to be interested in for all the models we look at today. Okay, so let's start with some motivation for why we are interested in this. This goes back to a phrase called the wisdom of crowds, a notion that collective decisions may be better than ones that individuals make on their own. There's a book, a fairly recent book with this title by James Surowiecki, where he discusses many examples of this. And one well-known example goes back to Francis Galton, who was one of the founders of statistics in Britain. Galton apparently was attending an agricultural fair, and there was a game at this fair. There was an ox, and there was a contest. People had to guess the weight of this ox, and they write down their guess on a slip of paper and put it in a jar. And the one who guesses closest to the true weight gets a prize. And Galton looked at all these slips of paper, and there was none of them was, they were all quite varied. There was a lot of variability. They were maybe not very good by themselves. But when he took the average of all these, he found that it was very, very close to the true weight of the ox. And on the basis of this, he conjectured that somehow there is some wisdom to the crowd, and they collectively know things better than any individual knows. Okay, you may or may not believe this. There is no particular reason in this context to believe that this should be true, but there may be settings in which this is a reasonable thing to expect. So that might be one motivation. We want to take collective decisions. And in fact, societies do take collective decisions. We mentioned this last time as well. So insects like ants and bees certainly do this. The whole colony decides where to go to forage for food, or where to go to create a new nest, and so on. But even very, very simple organisms like bacteria do this. And this is quite remarkable. You think bacteria can't do very much, communicate and make collective decisions, but they do. So there are these bioluminescent bacteria which can decide whether to shine, to emit light. And they make this decision only when the density of our other bacteria around them crosses some threshold. And so in the ocean, you can see these huge sheets of bioluminescent bacteria suddenly turning on and shining, and this is a collective decision. So we might wonder how such extremely simple organisms can make such decisions, and are there very simple decision rules which can give rise to quite complicated emergent behavior. Okay, so some more complex examples of emerging behavior are flocking in birds. So there are these big flocks of birds which decide which direction to fly in, and the flock moves as a whole somehow. But there is, at first, people thought there's a leader and everybody's following the leader. But in fact, it's quite hard to have visibility of any single bird from the whole flock. And it seems that who is the leader also changes quite quickly and unpredictably. So there's been work suggesting that the way these flocks happen is by the individual birds following some very simple rules of adapting to the average velocity in their neighborhood, but maintaining maybe some minimum distance with other birds, and so on. And so there has been some nice work on trying to come up with models and see if they replicate the behavior of observed flocks. There's a famous model by Vishek et al. On this problem. And similar behavior in fish as well, that's called shoaling. And in this example, which we won't discuss in more detail today, the network so as the birds move, the network of who is close to whom and who can interact with whom changes. So it's not only the values at the nodes, which are the velocity vectors, they are changing, but the network is changing simultaneously with these values. And that's a model we won't go into, but that's also a very interesting model. Okay, and then in human social networks, we might be interested in opinion dynamics. So how do people decide which political party to support, or what opinion they take on various issues in the news? And there is a lot of evidence that communities in fact polarize, and as a result, on questions which are maybe not so obviously related, they have similar views. So there may be something which is economic. Are you economically in favor of free markets or socialism? And are you on some social issue in favor of collective or individual behavior? Okay, maybe these are related, but there are other things which are perhaps less philosophically related, but nevertheless, these communities seem to have similar opinions, and understanding that could be an interesting question. And the final motivating example is algorithms in computer science, where we want to actually use these decision-making rules in large complex systems to ensure that the system coordinates on some task. So for example, we might have sensor networks maybe to detect forest fires, and any one sensor reading may change suddenly because the sensor is faulty or it's exposed to bright sunlight or something. And you don't want to decide there's a fire just because one sensor is now in bright sunlight. So you want to combine information from lots of sensors to decide this. There may be distributed databases distributed globally in which you want to replicate data reliably, achieve collective behavior, and some modern examples of this blockchain and swarm robotics, where you want to achieve this kind of coordination or consistency. And so you might try to design algorithms to achieve these things. So one is given an algorithm, understanding how the system evolves. Another is given the evolution of a system, trying to guess what sort of algorithms it's using, and finally designing algorithms to achieve what you want to achieve in terms of coordination. Okay, so these are all different strands of motivation for the kinds of models we are going to look at today. Okay, I'll start with a very simple model for averaging, and this model is due to a sociologist called Groot in the 60s or 70s. And this is mathematically the simplest model we look at today. So time is going to be discrete in this model. There's a finite collection of agents. They all have real valued opinions, some number. Okay. Maybe it's a number between 0 and 1. Maybe it's a temperature reading at a sensor. It's some real value. And these evolve as follows. So in each time step, what each of these agents is going to do is it's going to take an average of opinions of its neighbors. It may include some weight to its own past opinions. So the value x associated with agent I at time step t plus 1 is a weighted average of the values of agents j at time step t. Here I've taken the average over all agents j, but some of these weights will be 0. Maybe you can only interact with agents who are close to you. And so the weight wij says how much importance agent I gives to the opinion of agent j. It might give equal opinion to all its neighbors. It might trust some neighbors much more than others. So that can all be encoded in these weights w. Okay, so we can write this as a vector. So the vector, this should be boldface, x at time t plus 1 is the matrix W multiplying the vector of opinions at time t. And the assumption we are going to make is that W is a stochastic matrix. So all the weights are non-negative. You don't reverse anybody's opinion, or you may give them small weight, but you don't give them negative weight. And also the sum of the weights adds up to 1. You are dividing your total, you are averaging over neighbors you're taking a weighted average. Okay, and we'll further make the assumption that this an irreducible and aperiodic Markov chain. Explicitly, the opinions at time t are the weight matrix W raised to the power t times the initial condition. And so how does this behave? Well, this converges to the dominant eigenspace of the matrix W. It converges to the invariant subspace corresponding to the largest eigenvalue and absolute value. So that's what we want to look at. So what do we know about the eigenvalues of this matrix W? It's a stochastic matrix. That means that the all1 vector is a right eigenvector. If we do multiply W times 1, we are taking the row sums of W. The row sums are 1. So we get back the vector 1. W times 1 is 1, all1 vector. And so the eigenvalue is 1. Okay. So W is a positive matrix. The all1 vector is a positive eigenvector with eigenvalue 1. So what I want to claim is that means this is 1 is the largest eigenvalue of this matrix. And why is that true? Okay, so if we denote the other eigenvalues by lambda 2 through lambda n and arrange them in decreasing order by absolute value, then the Perron-Frobenius theorem tells us that the positive eigenvector corresponds to the Perron eigenvalue, the largest eigenvalue in absolute value. And all other eigenvalues are strictly smaller than 1. Okay. This strictly smaller than 1 depends on irreducibility and aperiodicity. So what happens if the matrix W is not irreducible? That means there are different communities, if you like, in this opinion dynamics model, and these communities don't talk to each other. Then they can't possibly reach a common value. This community may converge to one value, that community converges to another value. And unless your initial conditions were magically chosen correctly, these two values will be different. So you can't expect consensus in that case. And then the eigenvalue 1 is repeated. You have multiple eigenvalues of 1 corresponding to each community. If you have periodicity as well, then again this condition breaks down. If your matrix is irreducible but periodic, then 1 is a unique eigenvalue. This is not repeated. But what happens is that you have other eigenvalues on the unit circle in the complex plane. So if the period is 2, -1 is an eigenvalue. If the period is 3, the third root of unity is an eigenvalue, and so on. So you have other eigenvalues on the unit circle. And again, convergence is not guaranteed. What can happen is the opinion can oscillate. So if you have, say, a bipartite graph, then in alternate time steps, you are averaging this. This subset takes the average of that subset, and then that subset takes the average of this subset, and so on. And so the values oscillate. So again, you don't have convergence. So this can happen, but if you assume irreducibility and aperiodicity, then you rule out these bad cases, and you have the setting where the second eigenvalue is smaller than 1. Okay, and so in this case, the vector xt has to converge to the invariant subspace, which is now one-dimensional. It's just the span of the principal eigenvector, the all-bond vector. So xt converges to some multiple of the all-bond vector. And we can ask what multiple does this converge to, and we can answer that explicitly as well. Okay, so firstly, how quickly does it converge? It converges geometrically fast, so the error of xt from its limit decays to 0 like some geometrically fast as the second largest eigenvalue. And this gap between, so this is called the spectral gap, if you like. And so the spectral gap determines how quickly we converge to the steady state. And this constant C can be calculated explicitly. So it's the inner product between the invariant distribution pi of this Markov chain and the initial condition x0. Recall that pi is the left eigenvector corresponding to the eigenvalue 1. And so this is, again, just standard linear algebra. So this pi, you can check that pi times xt is preserved by these dynamics. Because pi times w to the t, x0, pi w to the t is just pi, so it's pi x0. So pi xt stays the same as pi x0 for all t. So pi times 1 has to converge to the same constant c. Okay, so this is very straightforward linear algebra. There was nothing much to do there, but this is just a starting point. Okay, so this is an easy model to analyze. So why was de Groot interested in this model? He wanted to answer questions such as, in a society, who is influential, who decides the final consensus reached by the group? And okay, if you believe this model of how opinions evolve, then the relative importance of different agents is given by this invariant distribution pi, because the final value c depends on pi times the initial values. Okay. Okay, and there are some special cases. So if you have an undirected graph and the weights are, each node assigns equal weight to all its neighbors. So it assigns weight 1 over its degree to each of its neighbors. Then you can check that the invariant distribution pi for this Markov chain is proportional to the degree. It has to be normalized to 1. It's proportional to the degree, and so the influence in this opinion model is also proportional to the degree. Okay, so this was very simple, but people have studied more challenging versions of this problem, and that happens whenever the graph is not static. The weight matrix is not fixed over time, but it's evolving over time, maybe randomly or maybe even adversarially. An adversary changes the weights over time to try and prevent you converging or to slow down convergence, and you can ask what effect the adversary has. Okay, and here are a bunch of references studying the dynamic versions. The static version is very classical. De Groot's model goes back to, I think, the 70s, but more recent work has looked at these dynamic versions. And so these are some, by the way, there's a huge number of papers on this topic. If any of you is thinking of research problems, the literature is enormous, and this is a very, very limited selection, somewhat arbitrary, from this huge literature, studying some models of dynamic or variants of these consensus algorithms or averaging algorithms. Okay, so that's all I want to say about averaging. I'm going to move on to the consensus problem, unless anybody has questions already.
Am I right that in this model, at the end, it will be only one opinion that's defined by the constant C?
Yes, there's a slight difference from this model from the consensus models we are going to look at later. This is averaging, so it gets closer and closer to C, but it never reaches C.
Oh, okay.
Okay, so yeah, it's deterministic and converges to C without reaching it. The later models will have a discrete set of opinions, so they will reach a common value at a random finite time.
Okay. Thanks.
Okay, so let's move on to those kinds of models. So the classical example of this is called the voter model. We'll start with the complete graph and then move on to general graph. So we have, let's say, a complete graph on n nodes, and each edge is bidirectional. There's an edge in each direction. The vertices now have opinions in a discrete set, and for simplicity, let's just take the set of two elements, 0 and 1. Nothing much changes if you allow more opinions. Okay, and now the model is going to be stochastic, and we are going to define it very similarly to the rumor spreading model we looked at last time. So we'll put independent Poisson processes of unit rate, one at each vertex, and we'll denote by n sub v the Poisson process at vertex v. And every time there's an increment in this process, the vertex v becomes active. It's going to change its opinion, and the way it does this is by choosing another vertex w uniformly at random. So it chooses who to communicate with uniformly at random. And then it simply copies the opinion of whoever it talks to. Okay, very simple. You have some opinion, you talk to somebody, and you then adopt their opinion. You are very easy to persuade. Your opinion is that of the last person you talk to. Okay, maybe unrealistic, but still a very simple model and a good starting point for analysis. Whether this was, I don't think this was ever proposed as a model for voter behavior, at least not initially. I think there's some recent work trying to use it as such. My understanding is that it was first proposed in the statistical physics literature to model spin glasses, but I'm not very familiar with the history of this model. Okay. But it was very much in the interacting particle systems literature that it was studied first. And I believe first on lattices, but we won't talk about lattices so much here, just finite graphs. The questions we are interested in this model are the same. So do they all eventually reach consensus on one of the values, 0 or 1? And if they do, how long does it take? And given the initial conditions, what's the probability that they reach consensus on one specific value, say 1? So these are the questions we want to look at. In fact, we'll look at this on a more general model, which I'll now introduce. So again, we have a set of n agents. Now let's directly move from putting the Poisson clocks on the edge, on the vertices, to putting them on the edges of this graph. So again, you should think of these n agents as being connected by some graph. So now there's going to be independent Poisson processes, one on each edge, VW. They may have different intensities, which we'll denote by Q sub VW. Okay, and if there is no edge, these intensities are going to be 0. If there's an edge, we'll assume it's strictly positive. And every time the Poisson clock on this edge VW ticks, agent V is going to call agent W and simply copy the opinion of agent W. So exactly as before. Okay, and then we are going to construct a matrix capital Q with these rates QVW on the off-diagonal elements. And on the diagonal, we are going to set it to be minus the sum of the off-diagonal terms, so that the row sums of this matrix become 0. And that means this is the rate matrix or the generator matrix of a Markov process. Okay, the off-diagonal elements are non-negative. The diagonal elements are negative, and the row sums are all 0. So this defines some Markov process on V, which is not the Markov process of interest. It is not the voter model, but we'll come to this. It'll play a role in studying it, and we'll come to it later. Okay. Okay, so the way I've described the voter model is a pull model. If I talk to you, I copy your opinion. You could equivalently define this as a push model. If I talk to you, then you have to adopt my opinion. And these are just transposes of the matrices, nothing much changes. So for definiteness, we work with the pull model. Okay, so now...
And what about initial condition at the 0 point?
Initial condition is given. Let's just say it's given. It's not all 0 or all 1, but somehow
okay.
It's otherwise it's not interesting, but it doesn't matter how it's chosen. We'll say we are going to calculate what happens as a function of the initial condition.
Okay, good. Okay, thanks.
Okay, so first thing to notice, so first we want to describe the evolution, the dynamics of the voter model, and you've probably guessed already that it's a Markov process because it's built on top of all these Poisson processes, which are Markov, which are memoryless. So the state of this model is the configuration of opinions at all the vertices V. It's the vector xvt for all V in V at time t. And how do these opinions evolve? So if x is the vector of opinions at some time, you can transition from this by the opinion of a single vertex changing. Only one vertex changes at a time because these are Poisson processes in continuous time. So what's the probability that vertex V changes its opinion? So the transition from x to x plus the unit vector at V happens if vertex V had opinion 0 and it changes to opinion 1. So how can it change its opinion to 1? It happens if vertex V contacts some other vertex W whose opinion was 1. And QVW is the rate for contacting that particular vertex. So if it contacts any such vertex, it changes. And okay, just to recall, we are using, in writing all this and saying this is the rate and this is Markov, we are using the fact that superpositions of independent Poisson processes are independent, and so that's why you get the sum of the rates, etc. Fairly straightforward, but just want to make sure that we are all on the same page here. Okay, similarly, if vertex V was in state 1, it can change to state 0 with rate, which is the sum of contacting all vertices in state 0. And these are all the transition rates of this Markov process. So this fully specifies the evolution of xt. And this seems like a complicated generator matrix to study. So there is little hope of maybe a very direct attack of trying to solve this generator matrix. So how are we going to study this system? So let's start with a very simple observation. What happens if all the opinions are 0? Then this state is absorbing because every time a node contacts some other node, it can't change its opinion because they have the same opinions. Similarly, the all-one configuration is absorbing as well. And if we start with the assumption, I should have said, I think I said it somewhere, or maybe I didn't. We are going to assume that Q is the rate matrix of an irreducible Markov process. So if we assume irreducibility, that means that you can access these states from every other state. Eventually, everybody can influence everybody else, and you can reach these from all states. Okay, so I've said this here. So this happens if the graph is strongly connected, meaning there's a directed path from every vertex to every other vertex. And that's the same as the rate matrix Q corresponding to an irreducible chain. So this means this is a finite state Markov process with absorbing states which are reachable from everywhere else. So eventually it has to be absorbed in one of these states. And that means that consensus is guaranteed in this model. Okay. So the questions we want to ask are, where does it reach consensus? How long does it take, etc.? And to do that, we need to study a different Markov process, not the water model. And that is going to be the random walk on the vertex set with the same rate matrix Q. Okay, so this is the rate at which nodes talk to each other. And now we are going to use that rate matrix to define the random walk on the vertex set. So there's a particle which is at vertex V. It moves to the neighbors of V. So there's a Poisson clock on each edge VW. And whichever clock ticks first, it'll move along that edge to its neighbor and repeat the process from that vertex. So it's a continuous time random walk. Okay. And if the graph is strongly connected, then this random walk is an irreducible Markov process on the whole vertex set. You can it can go from anywhere to anywhere. And so it has a unique invariant distribution. And let's call that pi. Okay. So now I want to claim that if you take this inner product of pi and the configuration xt of the water model at time t, then this inner product, which is a number, so mt is a number, so this process is a martingale with respect to the natural filtration. So if you keep track of xt, then with respect to that, this mt is a martingale. And that's going
Ganesh, sorry.
Yeah.
We have a question in chat. 1 second. Sergey asks, Ganesh, could you repeat the definition of the random walk?
Yeah, the random walk. So start at some arbitrary position V. The random walk is in continuous time. So we have these independent Poisson processes on each of the edges of the graph with these rates Q, V, W. If I'm sitting at vertex V, I look at all the edges around me. The first edge, which has an increment on its Poisson process, I walk along that edge. So I reach a new vertex, W. And from W, I do the same thing. I look at all the neighboring edges. Whenever the clock on some edge goes, then I walk along that edge. Does that answer your question?
Okay, I think, yeah, thank you. Evgeny want to say something?
No,
okay.
I think it's answered. Everything is okay.
Okay. Okay, so that's the random walk, and pi is the invariant distribution of that random walk. Okay, and then we want to claim that this pi times xt is a martingale. Why is that true? Okay, so this is a fairly easy calculation, but let's do it. So suppose we are in state x at time t, the configuration is x at time t, and tau is the first jump after t. So what's the probability that the configuration at time tau is x plus ev? So here were the rates of the jump from v to x plus ev. We wrote this down earlier. So the probability that the jump chain this is standard. The jump chain associated with the continuous time Markov chain is a discrete time Markov chain with transition probabilities proportional to the rates. So C is that constant of proportionality. And so you go to the state with probability proportional to the rate, and this should be chosen so that it adds up to 1. That's it. Okay, so these are the rates. And now what happens if the chain goes from x to x plus ev? The value of the martingale increases by pi v because that's how it was defined. It's the inner product of pi and the configuration. And if it goes to x minus ev, it decreases by pi v. So this is how much it changes with these probabilities. And so we can calculate the expected change in value of the martingale by adding these things. So if we add up all the rates, we get this sum. So we get pi v times qvw, and depending on, so the sum is over edges where v is in state 0 and w is in state 1. So if with this rate, v changes to a 1 and the martingale value increases by pi v. If v was 1 and w was 0, it decreases by pi v. So these are the rates. And now we add and subtract pi v q v w, the indicator that both are 0. Both v and w are 0. If we add and subtract that indicator, then we can rewrite the sum where we first sum over those vertices v where xv is 0, but now the sum over w is not just those where the value is 1, but now we are summing over all values, all vertices w. Okay, we've just changed the sum. So here we are summing over all vertices w. Similarly, in the second sum, we are summing over all vertices v. So it's just rearranging terms. Some simple algebra which you can go over in your own time. But now with this rearrangement, I want to claim that all the terms are 0. So let's look at this inner sum here. So we are summing over all w, pi v, q v, w. Let's pull pi v out of the sum. Now we are summing over the rates. So we are summing over the row of this matrix Q. The row sums of Q are 0. So this inner sum is 0 here. And so the whole sum is 0. Similarly, for the second term, if we look at the inner sum, we are summing pi v q v w overall v. So this is the wth element of the product pi q. Okay, but pi is the invariant distribution, so it solves the global balance equations. Pi q is the 0 vector. So because it's invariant, this inner sum is 0, and similarly, this whole sum is 0. Okay, so this whole thing is 0. The change in the expected value is 0 for arbitrary value of x. So conditional on xt equals x, the expectation is the same, and that means this is a martingale. So that's the proof that this is a martingale. Okay. Good. So this was the only calculated derivation involving calculations I wanted to do, more or less. Let's look at a few examples of this. So if we take G to be a connected undirected graph, and suppose we go to the analog of, we studied a similar model for rumor spreading last time, but the analog is the edges have, so the vertices become active at rate 1 and they pick a neighbor uniformly at random. That means you are putting rates 1 over the degree of V on each of the directed edges from V to W. Okay, so if you do this, then the Markov process with this generator is irreducible, and you can show that the invariant distribution is proportional to the degrees, and that follows straightforwardly from the fact that this, if you guess that this is the invariant distribution, you can check that it satisfies the local balance equations because pi v is proportional to the degree, qvw is 1 over the degree, and so both sides of this equation are 1. If there's an edge between v and w, and if there's no edge, then both sides are 0. So either way, these detailed balance equations are satisfied. So this is the invariant distribution. Okay, so in this case, you can explicitly calculate the martingale. So this is just the sum of the values at the individual vertices weighted by their degrees. And that gives you the martingale, and the special cases are d-regular graphs or the complete graph, which is n-1 regular. Good. So these are some calculations. And we have obtained this martingale associated with the water model. And why did we go to the trouble of doing all this? You might have guessed. So we want to the question we are trying to answer is, what's the probability of reaching consensus on different values? And to answer this, we are going to use the optional stopping theorem for martingales, and that's why we are doing all this work. Okay, so some preliminaries before that. So okay, what am I doing here? I'm just defining some things formally. So we already saw that we are sure to reach consensus at some time, but that's a random time, capital T. So this is the first time that the state is either the configuration is either the all 0 or the all 1 state. And this is finite almost surely if we assume that the matrix Q is irreducible, or equivalently that the graph G is strongly connected. And what we want to calculate is the probability that, let's say, we reach consensus on the all 1 state. And let's denote this probability by alpha. And this is what we want to calculate. Okay, so now the optional stopping theorem for martingales tells us that the value of the martingale at this stopping time, okay, it's easy to see that capital T is a stopping time, and the value at the stopping time is the same as the initial value. So the value at the stopping time is the inner product of the invariant distribution pi for the random walk and the configuration xt. And this is our initial condition. Do I have one more slide? Okay. Okay, so what's the left-hand side? Xt is either the all one vector with probability alpha, in which case pi times the all one vector is 1. So we get 1 here with probability alpha. Or xt is the all zero vector, in which case this takes the value 0. So it's 0 with probability 1 minus alpha. So the expectation is just alpha. So that's alpha. Okay, if we start in some deterministic initial condition x naught, the right-hand side is just pi x naught. So this gives us the hitting probability. Okay, so we can calculate, given the initial condition, how likely we are to reach consensus on all ones or all zeros.
Just small type. Alpha, in the definition of alpha, it should be capital T. Yeah? Probability.
Thank you. Yeah, capital T. Thanks. I should correct that. Yeah. Okay. Thank you. Okay, so this is the answer to the first question we are interested in about hitting probabilities. And okay, you may recognize that this looks a little bit like what we saw in the de Groot model. This was the common, so there the values were real numbers, but we approached consensus on some common real number, which was pi times x naught. Here, they are not real numbers, they are discrete, 0 or 1, but here we reach 1 with this probability and 0 with the residual probability. So they look somewhat similar, and that might ask you to wonder, might we have been able to guess this answer more easily without using martingales and so on? And in fact, we could have guessed the answer. So this is just a different approach to deriving the same result. So the random variables x, v, t are discrete, but if you look at the expected values, you can write differential equations for the expectations. And this is the differential equation in vector notation. The expected value at some vertex is the average of the expected values at its neighboring vertices with these rates. So, okay, there may be no change, but with some probability, it copies its neighbor and changes. So these are the rates. So you have a continuous time analog of the de Groot recursion. You can solve this a linear differential equation. You can solve it. So expectation of xt is e to the qt times its initial value, which we take to be deterministic, and x naught. So this is what happens at time t. So as t goes to infinity, you know what happens to this. So as t goes to infinity, e to the qt converges to a rank 1 matrix, which is the outer product of pi and the all one vector. And so because it's irreducible, and so ext converges to some constant multiple of the all one vector, which is given by this. So this is now in continuous time, and this is for expectations. We are not talking about the random variables xt, just about the expectations. Now you still have to separately observe. This doesn't prove that the random variables xt themselves converge. They may just oscillate with this expectation. But we know separately that the Markov chain has to converge, has to hit one of these absorbing states, which is either the all one or the all zero state. And you can use that fact to say, if it hits the all 1 state with probability alpha and the all 0 state with probability 1 minus alpha, then that is consistent with this only if alpha is exactly this value. So you can also reach the same conclusion without using martingales, but writing down a differential equation for the expectations and solving it. Okay, so that is hitting probabilities in the water model. Okay, and then we'll take a break, and after the break we'll talk about the time to consensus. How long does it take to reach consensus? Okay, so it's nearly 11 o'clock. Should we meet at 11:10 or 11:15? When should we come back?
I think 11:10 will be fine, but first of all, thanks Ganesh for the first part. Yeah, it seems that Pasha has. Okay, Pasha is here. Okay, should we already applause? Yeah, for the first part.
I think yeah.
Thanks.
Thank you.
So I just need to remind that if you don't understand anything, you should ask question to Ganesh in chat here on orally and so on. For me, it looks fine. I don't know. For me, it looks fine. Everything is clear. Pasha, what about you?
Yeah, but I have some problems with my internet connection, so I didn't hear all the lecture.
All the lecture, part of the lecture.
Part, yeah. Sorry.
Okay. So, and let's see each other in 13 minutes. Yeah. So
Yeah.
at 11:10 in British time.
Okay.
Okay. See you.
See you.
Super.
Oh, sorry, Ganesh. I just said that essentially you said you use some random walk in continuous time, yeah?
Yeah.
But in terminology, what I use, for example, is Markov jump process. Homogeneous time Markov jump process. Correct?
Yeah. In talking in general,
it's possible.
Chains and
It's
processes.
inconsistent terminology. Yeah, people are.
Yeah.
Ganesh, may I ask a question? In the water model, what we have that after some time, V copies opinion from W, some another vertex. But other exist models when V copies this opinion with some probability, maybe with given probability.
Okay, good. So the first thing you could do is, indeed, look at this. Should we wait for everyone or to answer this question, or shall we start?
Yeah, I think we can start.
We can start. Okay, so I'll answer to everyone. Yeah. So that's indeed one way to modify the model, to say that I talk to you and I copy your opinion with some probability. But as long as this probability is fixed and doesn't depend on our opinions, then it's the exact same model, because all that happens is that you are thinning the Poisson process when I copy you. And still it stays a Poisson process. So the rates change, but nothing else changes. It's the exact same model. But if the copying probability depends on whether you agree or disagree with me, then of course, then it's a very different model.
Okay, thank you.
Okay, are there more questions, or should I start sharing screen?
Yeah, yes, I think we can start. Second part.
Okay. Okay, so now we are continuing to look at the water model, but now we are interested in the time until we reach consensus. So we define this random variable capital T as the first time of hitting either the all 0 or all 1 state. and we want to know what we can say about this time. It turns out that we can calculate this pretty exactly on the complete graph, but only on the complete graph. In general, we can only get upper bounds, and on some graphs these are good, and on some others they are not so good. But the upper bounding technique itself is very interesting. So that's what I'm going to talk about, first on a general graph, and then we can just apply the result, specialize it to the complete graph. And this technique uses dual process. So we look at the water model backwards in time, and when we do that, it looks like a system of coalescing random walks, and that's what we use to bound the time to consensus. So this is a very interesting technique, and the first reference to it I've seen is in work of I believe Dominic Welsh and Andrew Barbour. I don't know who first came up with this. I should really check this more carefully. But okay, so this is some quite interesting work. So let me, so this is going to be quite pictorial. So here I'm looking at a very small network with 5 nodes. It's complete. They can all talk to each other. Time is going from top to bottom. So forward time starts here and goes down the page. Backwards time will start at the bottom and go up the page. And so these arrows indicate who talks to whom at different times. So these are the initial beliefs we start with. And then voter 2 talks to voter 5. Agent 2 talks to agent 5, copies its opinion, which is the same, nothing changes. Then 1 talks to 3, changes to a 1, etc. You can look at what happens forwards in time and decide at the end whether they all have the same opinion or they have not reached consensus yet. What we are going to do instead of doing it that way is we are going to start backwards. So we are going to start at the end, work our way backwards and ask have they reached consensus. So let's do that. So I'm going to keep track of things by putting a particle at each of these vertices. So these are the blue particles. The color doesn't matter. So these are the particles, and then I'm going to move backwards in time. Okay, so backwards in time, what happens first? Agent 3 talks to agent 4 and copies the opinion. We don't know what the opinion of agent 4 was at this time, or maybe we do, but never mind. We haven't watched it forward, so we don't know. But at this time, what we know is that anything that happened to agent 3 before this time is irrelevant. Okay. The opinion of agent 3 at the end only depends on what happened to agents 1, 2, 4, and 5 before this. Agent 3 is irrelevant. So let's show this in the picture by going to the next slide. So I have now moved above the last arrow. I've moved all the particles, but I've got rid of the particle at 3. This red says there's no particle here. Okay, so because what happened to 3 before this time is irrelevant. Instead, I've taken the particle from 3, moved it to 4, and merged it with the particle at 4. In order to know what happens to 3 at the end, it's enough to keep track of particle 4 before this. So I've moved the particle to position 4 and merged it there. And I've put this red light here to say that influence from before this cannot propagate to after this. It can't cross this red light. That's what this picture is saying. Nothing that happens to agent 3 before this time is relevant. Okay, all this is irrelevant for the final state of agent 3. Okay, and then we are left with these 4 particles, and let's continue this process. The next thing that happens is agent 5 is talking to agent 1 and copying agent 1. So anything that happened to agent 5 before this time is irrelevant. Okay, so we can forget agent 5. I'm going to move this particle to 1 and get rid of this particle. Okay, so I've got rid of this particle here. I've put a red light and it's moved to 1, location 1, and merged with that particle. And so we have to keep track of these 3 particles. And I'm going to keep doing this. Okay, the next thing that happens is that 3 talks to 5. Okay, but there's no particle at 3 by this time because this particle has moved elsewhere. So what happens? So this is irrelevant to the future. So this arrow has no effect, and I just move past it. All my particles move past it. Nothing changes. Sorry, which way am I going? Yeah. So I've moved all my particles above it. Nothing happens at this time. Okay, next thing, agent 1 talks to agent 2 and copies it. So what happened to agent 1 before this time is irrelevant because it's copied agent 2. Wrong way. Yeah, so I've got rid of agent 1. It's moved, the particle has moved to 2 and merged with it. I'm just now keeping track of only 2 and 4. I continue going. Okay, so yeah, what happened now is that 4 talks to 2 and copies 2. So the particle from 4 moves to 2, and nothing that happened to 4 before this time is relevant. Okay, so now I just have particle here. And then what happens at this time? 1 talks to 3. There's no particle at 1. I don't have to do anything. And then 2 talks to 5. Okay, and copies 5. So again, I repeat this process. Now the particle from 2 moves to 5. There's nothing there to merge with, but that's fine. It still moves to 5. And then I put a red light at 2. Okay. So when I've done this process backwards in time, for this particular set of arrows, it so happened that I had just 1 particle left. For some other realization of these arrows, I may have had more particles left. And it would depend where those particles are as to whether consensus has been reached by the end or not. In this case, there's only 1 particle left. It's at position 5. So what this says is that every particle at the end got its opinion from this location. It got the opinion of 5, so its opinion is 1. So that's what the backwards in time process has told us. If there were 2 particles and they happen to be at 3 and 5, it so happens the opinion is the same. We are lucky in that case, and that still proves consensus. If they happen to be at 1 and 5, they have different opinions, so consensus has not been reached. So that's the picture. Okay. So now going back to this picture, if you want to know what the opinions are at the end, you just follow from top to bottom. So you can go down a black line, you can go down these timelines, but you cannot go past a red light. You can walk along arrows, but in the red arrows, but in the opposite direction. So you can start from 5, you can walk this way along this red arrow, and then you can reach the end here. So you know that the opinion of vertex 2 came from 5 this way, and this way. So the opinion of vertex 2 is 1. If you're interested in the opinion of vertex 4, you start at 5, you walk the wrong way down this arrow, you come here, walk the wrong way down this arrow, you come down, etc. So you can work out based on these what all the opinions are. So just you can go down the black lines, you can walk the wrong way along the red arrows, but you cannot go past one of these red lights. Those are the rules. Okay, so hopefully the picture is clear. The construction of the backward time process is clear. So we can always guarantee consensus if the backward in time process started at some time t here. So this is going to be t. Started at time t, achieves coalescence to a single particle by the time we come back to time 0. So here this already happened at this time. So we already could have known at this point that we have reached consensus without even continuing, but okay. In general, you have to continue all the way to decide whether there's consensus. Okay, so in order to find the time required for consensus, rather than study the water model forwards in time, we are going to study this coalescing random walks backwards in time. So that's what we'll do. Okay, so this was the final configuration. Okay, so the coalescing random walks process. So I'll just describe formally what I said earlier. So we start with one particle at each vertex. How do these particles move? So let's go back. So the particle moves whenever it encounters a red arrow. And what are these red arrows? These are the rates at which some vertex V talks to some vertex W. So if this is V and there's a particle here, when it sees this red arrow going at rate W, it follows the red arrow and goes to this vertex and merges with the particle there. Okay, and of course, Poisson processes are reversible. So if I watch this Poisson process, it doesn't matter whether I'm doing it forwards in time or backwards in time. So these particles perform independent random walks, continuous time random walks, or if you prefer, Markov jump processes governed by this rate matrix Q. Okay, so the particles are jumping independently in continuous time according to this rate matrix Q. And now if a particle at some vertex jumps to another vertex which is already occupied, then it merges with the particle there and they become one particle. And that's it. All we care about is the particle. It has no weight. Its movement doesn't depend on its weight or anything. It just continues to move like a single particle. Okay. Yeah, the merged particle behaves just like a single particle and performs the same random jump process. And then we want to count how many particles are left in the system at time t. Okay, we also have to keep track of where the particles are to describe this system. That matters, but let's just look at the number. In terms of the number, we can define the random time capital T to consensus in the water model. So the probability that consensus has not happened by time little t. So if consensus has not happened, that means that if you started at little t and work backwards to time 0, there must be at least 2 particles left. Okay. So, but these random walk processes are the same backwards in time or forwards in time. So the probability is the same that if you started this particle system, the probability that t time units later you have at least 2 particles. Okay. You might be lucky, you might end up with 2 or 3 or 5 particles which are in initial locations which have the same opinion, and so you have reached consensus. But that may or may not happen, whereas if there's just 1 particle, you are guaranteed to reach consensus. So an equivalent way to say this, if we define by t tilde the first time that we are left with 1 particle, then the consensus time is stochastically dominated by t tilde. Okay, so t tilde gives an upper bound on the consensus time. Okay, so that's the equivalent model. So instead of looking at t in the water model, we look at t tilde in this coalescing random walk model, and that gives us a bound on the time to reach consensus. Are there any questions on this? So this idea is the substance of is the key idea, and then it's just easy calculation.
Maybe just one comment, but you already mentioned it, that we can start random walk from the 0 point at time 0 and look what will happen at time t. But also we can start at time t and go backward and look what happened at time 0.
Mm-hmm.
And we will have the same random walks in distribution, that the distribution will be the same at the end.
Mm-hmm.
Am I right?
Yeah. But it's the random walk backwards in time that corresponds to the water model forwards in time.
Okay.
But now, okay, so that's how we start. Then we come to the random walk, and then we start analyzing the random walk. At that point, we have forgotten about the water model. We just want to analyze these coalescing random walks. Okay, and now I say, let's not fuss about whether it's forwards or backwards in time. This random walk is reversible, so let's think of it as, for convenience, it's just for convenience, as forwards in time and coalescing.
Okay, thanks.
Okay. So we can do very explicit calculations for the complete graph. In general, we cannot. We just have this bounds for this for these coalescences. But let's do the calculations for the complete graph on n vertices, and the rates are going to be 1 over n minus 1. Let's say you're equally, you have total rate 1 of jumping, and you choose a neighbor. You choose another vertex uniformly at random. All other vertices are neighbors. So let's define tau k to be the first time that there are exactly k particles left. And the nice thing about the complete graph is that it doesn't matter where the k particles are. That's what makes it much easier to analyze. Everything is symmetric, so the k particles could be anywhere, we don't care. So tau n is 0. At time 0, we start with n particles, and we are interested in tau 1, the first time that there is exactly 1 particle left. So now the taus, as time proceeds, k is decreasing. K is not increasing, k is decreasing. So it decreases from n to 1, and you want to know how long it takes. Okay, so when there are k particles, how quickly do these mergers happen? Each particle is moving independently at these rates. Now, a merger happens only if a particle moves to an occupied vertex. If it moves to an unoccupied vertex, nothing happens. The number of particles is the same. If there are k particles, there are k choose 2 edges between them, but direction matters as well. Either this particle could go there or that could go here. So there are k times k minus 1 directed edges, and with this rate 1 over n minus 1 on each of them. So the total rate at which these mergers happen is k times k minus 1 divided by n minus 1. Everything's driven by Poisson processes, so this time is exponential with this parameter. And so its expectation is the reciprocal of this rate, which you can expand in partial fractions. It becomes this. And the next step is much the same as we did for Rumours spreading. We can write tau 1, which we are interested in, as a telescoping sum. So tau 1 is the sum of tau 1 minus tau 2 plus tau 2 minus tau 3, and so on up to tau n, which is 0. So it's the sum, the expectation, bilinearity of expectation is the sum of these things. And everything cancels out except the first term, and you're left with n minus 1, or maybe n minus 2. Yeah, I think there's a slight error. There's maybe a minus 1 from the last term, and it's n minus 2. But okay, essentially, it's n. N is large, that's what we are interested in. So the time to reach consensus scales linearly in n on the complete graph. Okay. So I've tried to choose the parameters in this model to make it just like the rumor spreading model of last time, so that it's a fair comparison. The rate at which nodes are communicating with each other is the same. Rate 1 in total for a vertex, or 1 over n on each edge. 1 over n, 1 over n minus 1 are the same. Okay. So in the same scaling, comparing like with like, we saw last time that rumor spreading is very fast. It takes time only logarithmic in n. So in a huge population, you can spread a rumor in time logarithmic in n. But consensus is much slower. It takes time linear in n. Okay. Okay, and that's not intuitively, that's not hard to see. If you look at what's happening on the complete graph, rumor spreading is a process that happens in one direction. It's like a random walk with drift. With consensus, if you have some random number of 0 and 1 opinions on the complete graph, then you are equally likely to change a 0 to a 1 as a 1 to a 0. Because you can first pick the direction of an edge and then pick the direction along the edge, and you can see that that's what happens. So the number of zeros or the number of ones evolves like a diffusion, or evolves like a simple symmetric random walk. And we know that the time to hit the boundaries in a simple random walk grows quadratically in n, grows like n squared. But there are n things happening at a time, so in fact it's n. But this is just very loose reasoning to get the scale, understand the scaling, where the scaling of n comes from. It comes from the diffusion scaling of the number of zeros or ones. There is no drift there, there is only diffusion there, and that's why it's n. And this will be important when we later look at some slight variants of these models, where in fact you can get convergence in log n time by giving this random walk a drift towards the boundaries. Okay, we'll come to that later. Okay, but this is pretty much all. Yeah, so this completes the discussion of the time to reach consensus. So we did three things. We described a general method, which was relating the voter model forwards in time to coalescing random walks backwards in time. And then we said that if we can calculate this coalescence time for these random walks, then that gives us an upper bound on the consensus time in the voter model. And in fact, we can use that approach to get bounds in general. I'll comment on this in a little bit, but it's only on the complete graph and a few other special cases that we can do very explicit calculations like this and get exact answers. Okay, are there questions? No?
No, everything
Okay,
is
so,
fine.
yeah, go ahead.
I think, thank you.
Pasha said that everything is fine.
Everything's fine? Okay, good. So in the remaining time, so this finishes the discussion of the main voter model. I'm going to look at lots of variants of the voter model and say, and different application areas in which they arise. Okay, but first sticking with the voter model itself, so far, and most of what I talk about will be on finite graphs. But the origin of this whole subject was on infinite lattices. So let me say a bit about what we can say on lattices. So now G is going to be ZD or ZD, the integer lattice in D dimensions. And let's put rates 1 on all the edges. Now, because on a finite graph, consensus was guaranteed. If the graph is connected, everybody has to have the same opinion. With infinitely many nodes, this need not happen. Okay. And what we want to know is what happens in the long run. Do we eventually reach consensus, or do different opinions coexist. Okay, how do we make this precise for infinite graphs? So if you fix any two vertices, for an arbitrary choice of these two vertices, is it true that there is a last random time at which they have different opinions? So if you go far enough forwards in time in the voter model, can you say after this time they will always have the same opinion? Okay, and the answer depends on dimension, and this seems quite hard to answer, but the random walk, coalescing random walk construction helps us to answer this quite easily. So in forwards time, they eventually reach the same opinion. If backwards in time, the random walk starting at U and V meet. If they are guaranteed to meet, that means eventually they both get their opinion from the same vertex, and therefore they will always be the same. Okay. And that question, so you can have two random walks starting at U and V, or you can look at the difference, which is just one random walk on the d-dimensional lattice. And we know that these random walks are recurrent in 1 and 2 dimensions and transient in 3 or more dimensions. So asking if two random walks meet is the same as asking whether their difference hits 0. And so, yeah, if it's recurrent, it does hit 0. And so that says that consensus is reached in 1 and 2 dimensions. But in 3 or more dimensions, it's transient. So with some probability, you never hit 0, which means with some probability, you always, you evolve independently and your opinions can be different. Okay, so that construction helps us answer this interesting question about the voter model on the integer lattice. Okay, so other models to which the voter model is related arise in population genetics, and there are two versions in discrete and continuous time. The continuous time version is called the Moran model, and the discrete time is called the Wright-Fisher model. Okay, so and the voter model that we studied is the same as exactly the same as the Moran model. So we can think of a population of n individuals, or maybe it's better even to think of n genes. It doesn't matter very much. So you have a population of n genes. The population is going to stay constant over time, but it's going to evolve as follows. So, okay, so we are looking, a gene can be one of two types. So, which we'll denote by little a or capital A. And there's some language in biology, so these types are called alleles. So the gene can be either a little a allele or a capital A allele. And the kind of question biologists are interested in is you start out with a population in which everybody was originally little a, then some mutation happened and a capital A arose, and then how widely is this going to spread? Is it going to take over the whole population? Is it going to die out? What happens? So those are the kinds of questions. And quite often, okay, there are many reasons, I guess, biologists are interested in this, and I'm certainly no expert, but I think they also want to go backwards in time, looking at the prevalence of different genes in populations today and work out where these populations came from, what was their history of migration, etc., etc. So there are some very interesting questions here, and this is just the baseline model of, actually these are used very widely. These may seem ridiculously simplistic models for biology, but these somehow seem to be the underlying stochastic models they use, on top of which various other things happen, and there is data and they can use that. But the underlying model is basically the voter model. And so how do these genes, how does the population evolve over time? So in the continuous time version, in the Moran model, each individual dies at rate 1, independent of the other. So one gene gets killed, but the population stays constant over time. So every time you kill a gene, you pick somebody else uniformly at random and make a replica of their type. So a little a dies and copies either a little a or a capital A, chosen uniformly at random. But this is exactly the voter model. You pick some other vertex, you kill your own opinion, and you copy their opinion. And that's it. Okay. And so what biologists care about is, okay, what's the probability of fixation, which means that eventually everything becomes capital A, the mutant type, or of extinction, that everything eventually is little a, the wild type. And the Wright-Fisher model is just the discrete time synchronous version of this, where a whole generation evolves simultaneously. So you start with some generation, the next generation has the same vertices. From each vertex, you draw an arrow to your parent in the previous generation. Each child chooses its parent uniformly at random in the last generation and copies the type of the parent. And everybody does this in parallel. That's the Wright-Fisher model. Okay, and these are models for so-called neutral evolution. And by neutral, what we mean is that there is no selective advantage to the type little a or capital A. These genes are equally fit. We'll soon see a version where they have different fitness, and then you can ask the same question. If capital A is fitter, is it, okay, what is the probability that it becomes fixed in the population, that everybody becomes capital A after some time? But okay, many mutations are neither unfit nor fit, and then this is called genetic drift. Drift in random walks means moving in a direction. Drift to biologists means no preference in direction. It's what we call diffusion is what they call drift. So it's important to keep that in mind. Okay, so that's something about population genetics. This backwards in time coalescing random walk that we discussed is called the Kingman coalescent. So it gives a random edge-weighted tree where the weights are how much backwards in time you have to go before the coalescences happen. And this tree, this random object, is interesting in itself. That's called the Kingman coalescent, or sometimes the term is used for an infinite n limit of this. So if we set the edge rates to 1 instead of this, then the expected coalescence time is 1. It doesn't depend on n. So what happens is you can formally take a limit of these models. So somehow you start out with infinitely many particles at time 0, and pretty much instantaneously lots of coalescences happen. So in no time at all, you have come down to finitely many particles. So this is a very strange kind of Markov process. You can't even define it. So you can't, it has no generator backwards in time. But then once you're down to finitely many particles, then these coalesce much like we studied, and you can look at various properties of this, and that's also called the Kingman coalescent. Again, I'm not an expert on this, so I can't say very much more than that, than to say that this is again a very interesting object to study, and there's a huge literature on it. Some more models biologically interesting. So there's the infinite allele, so the Kimura-Crow model, and I thought I should mention as well. So in the voter model, we started with 2 opinions, 0 and 1. Nothing in our analysis really changes if you have any number of different numbers of opinions. So for example, if everybody starts with their own opinion, they are in the set 1 to n, then you are equally likely to reach consensus on any of these opinions. So you get 1 over n probability. Okay, or on a general graph, it depends on the vertex. It's the probability of reaching consensus on opinion V is pi of V. The time to consensus is exactly the coalescence time of these backward random walks, so nothing different so far. But in addition to copying opinions in this model, you can also have mutations happening spontaneously, and these happen at some rate lambda over n. And every mutation gives rise to a new opinion. You cannot go back to a previous opinion. Okay. And then in this model, which has both the voter model plus these extra mutations, you can ask how many distinct opinions in steady state are there in the population? What are the fractions of the populations with different opinions, etc. And these are biologists Kimura and Crow, and they were interested in this from trying to explain how much variability is there in a given gene in a population, how many different alleles are there, what proportion of the population has these different alleles, etc. So there's this other model in population genetics. Okay, so this is a somewhat tenuous connection, but I think it's a very interesting one, so I'll mention it as well. So there's this very nice algorithm for Monte Carlo simulation called the Prop-Wilson algorithm. So in general, we often have to face the problem of wanting to sample randomly from some distribution pi, either on some high dimensional space or on a discrete space, which is very large, some combinatorially large set. And this is very difficult to do, obviously. And one widely used method for doing this is what's called Markov chain Monte Carlo, or MCMC. And here what you do is you try to construct a Markov chain for which this target distribution pi is its unique invariant distribution. And then you simulate this Markov chain. And if you do it for long enough, the hope is no matter where you started, you are close to pi, you've reached close to the invariant distribution. And so a sample from this Markov chain taken after a long time gives you something approximately from pi. Okay, and constructing such a Markov chain is not hard usually, but knowing how long you need to simulate it is hard, because that depends on the mixing time of the Markov chain, and it's very hard to calculate the mixing time of a huge Markov chain on 2 to the 100 states or 2 to the 1,000 states or whatever. And it's also hard, while it's easy to construct the chain to have pi as the invariant distribution, making it rapidly mixing is hard again. It may take larger than the age of the universe to converge. So that's also a problem. But okay, let's just address the question. Suppose it does mix quickly, but how do we know when to stop? We still don't know how quickly it mixes. And what Prop and Wilson proposed was to do this by coupling from the past. So suppose the state space is finite, that's when this works most directly. Now we start parallel versions of the simulation. So you want to get a sample at time 0 in stationarity. Think of starting the simulation at time minus t and running it till time 0. And you want to know if the sample at 0 is in stationarity. And the point is that if you start parallel versions from every possible state, and if they have all coalesced by time 0, then necessarily they must have mixed. Because you can think of a simulation starting from one state and a simulation starting from pi, and if they meet, then they are in the stationary distribution, because the simulation started from pi is always in the stationary distribution marginally. So if you do this for all possible states and they have coalesced, then you have reached pi. And if they haven't, then you start from minus 2t and take a fresh sample and so on and repeat the process, and eventually you reach convergence. Okay, this seems a strange thing to do, because I started by saying the state space is huge. There are 2 to the 1,000 states. Obviously, you don't want to run 2 to the 1,000 simulations. Then you wouldn't even be doing, if you could do that, there are easier ways surely to simulate from pi. Okay, so you don't quite want to do this, but some models have a very nice property, which is that there's an order relationship on the state space which these Markov chains, so you can couple these Markov chains so they obey this order relation. And then you only have to start from the maximal state and the minimal state and run 2 parallel simulations. And if these 2 have met, that means that everything in between has also coalesced. So Prop and Wilson used this to simulate from the Ising model at criticality. The Ising model far from criticality is apparently easy to simulate, but at criticality was very hard. People didn't know how long it takes to mix, and they use this method to do this. And the Ising model does indeed have this monotonicity property. So if you start from all plus spins and all minus spins and simulate these 2, and if they have met, then every in-between configuration has also met. So that's the idea. So they were the first people to actually reliably simulate from the Ising model at criticality using this method. Okay, that was a bit of an aside, but it seemed slightly related and interesting, so I thought I'd mention that. Yeah, I spoke about the Moran model with selection, so this is much the same here. So you have 2 alleles, there are n-1 wild type, that's a spelling mistake, A with fitness 1, and a single mutant with fitness R bigger than 1. If it's smaller than 1, then it dies out with high probability. We don't care. So we want to ask, does this fitter gene eventually take over the whole population? And then it's the same Moran model. Okay, so how does fitness affect the Moran model? So in each step, okay, we kill a randomly chosen gene, but we pick a gene weighted by fitness. So for each copy of capital A, we choose it with probability proportional to R, which is bigger than 1, and each little a with probability proportional to 1. Okay, so if we do that, then we can calculate the probability of fixation. And it turns out that it tends to this constant R-1 over R as the population size gets large. And this constant is bounded away from 0 uniformly in population size. Okay, so no matter, whereas if R equals 1, then the probability of fixation is 1 over n. It's decaying to 0 with the population size. Whereas if you're even a little bit fitter, you can take over the whole population. Okay, and so this was for the Moran model on the complete graph, but in fact, this is also true for regular graphs. That was shown not so long ago. And then doing this for general graphs is an open problem, and that's potentially an interesting research question. Then some other couple of final variants of the Water model. So I said one of the uses of the Water model is in computer science to ensure that, say, in distributed databases or in robot swarms, everybody reaches consensus. There you want to reach consensus quickly, and quite often you want to reach consensus on the majority value. If you have, there may be some errors in updating your databases, so you want to ignore the errors and take the majority value and do it quickly. So are there versions of the Water model that can achieve this? So the Water model is slow, it takes time n to converge, and its probability of reaching the majority is only proportional to the majority. It's not very high. So one model that was proposed to do this was a 3-state voter model. So here you have the belief 0 and 1, and you also have this undecided value E. And the way this evolves is if I hold opinion 0 and I call you and you have opinion 1, I don't copy you. Because our opinions contradict each other, I don't copy you, but I just say I'm undecided. And if I have a firm opinion and I contact somebody who's undecided, I keep my opinion, I don't change. But if I'm undecided, then I copy whoever I talk to. Okay, so this is a variant of the question Pasha asked. So you don't have a probability of changing state, but you go through this intermediate state, which does this. And so we can ask what happens. So suppose state 1 is a minority initially. It's only a fraction smaller than 0.5 of the population. Then the probability of reaching consensus on this minority state is decaying exponentially in the population size n. And the decay rate is given by this entropy term. So H is the Shannon entropy function. Okay. So depending on how far, if P is exactly a half, then HP is 0 and there's no exponential decay. But as soon as P moves away from half, H is strictly positive and you have exponential decay of reaching consensus on the minority value. And also you reach consensus very quickly in logarithmic time. And there's another version of this. You can also do this in a majority model with polling. So here what a node does is instead of contacting one other node chosen uniformly at random, it contacts, say, 2 other nodes chosen uniformly at random. And then it takes its opinion and the other 2 and takes the majority. Or to put it another way, I only change my mind if I talk to 2 people who have a different opinion, not if I talk to 1 person who has a different opinion. Okay. Okay, and then you have exactly the same result. You get the probability of reaching consensus on the minority value decays exponentially with the same rate, again, log n time to consensus, and you, etc. And you can generalize this model further. Okay, couple of last things. Sorry, I'm running slightly over. A few more minutes. So, okay, so everything we studied, consensus was reached so far, at least in the finite cases. But often in social networks, this is not what happens, and we don't always want to models which yield consensus. We also want to ask, are there models in which different opinions persist forever, and maybe there's even polarization of opinions over time, and the network splits? One model that captures this is to start with some connected sparse graph. It's partly like the voter model. So when U contacts V and V has a different opinion, then U copies V. And this happens with some probability P. What happens with the remaining probability is that instead of changing the opinion, it changes the network. So with the remaining probability 1 minus P, if I talk to someone who has a different opinion, then that person is no longer my friend. I break the edge to that person and I form a new friendship with somebody else. So the total number of edges is preserved, but I form a new friendship. And then there are simulation results. As I think there are also some analytical results more recently on this model, but there were lots of simulation results showing there's a sharp transition that this model exhibits in this probability P. So if P is above some model, then you achieve consensus. If P above some value, you achieve consensus. If it's below some value, the network breaks up into zeros and ones. And so there are some very interesting results here, only partially proved. Okay, and then you can also have signed networks where depending, you have friends and enemies and you copy your friends and you take the opposite opinion of your enemies, etc. Okay, and these are some other interesting models to study. Okay, so I'll end with, again, there's again enormous literature on this, and this is a very, very small selection. So the first two of these look at deriving bounds on this coalescing random walks on general graphs, general matrices. So this is the model which looked at the Moran model with selection that I talked about and gave results for that. That's the three-state voter model. This is the majority polling model. And this last paper is looking at this dynamic voter model where edges change over time. Okay, so that's the end of today's lecture. And I'll take questions.
Okay, thank you very much. First, let's thank Ganesh for this beautiful lecture. I think all participants should turn on their videos and thank Ganesh for this lecture.
Thank you.
Yeah, I think Ganesh may stop sharing the screen that we can like talk to each other.
Yeah, okay.
Okay.
If I'm right, then at the start of today's lecture, you said about birds, about flocks. Yeah, that they go inside one flock and move all together in one direction. And did we touch today some model for this or not yet?
No, we didn't. So I'm not going to do that. I don't know if, yeah, there is a famous model due to Vishek. It's very different from the spirit of what we looked at today. It's a differential equation model, quite different. So I don't know of something that fits neatly in the framework of what we looked at today. I guess the dynamic voter model that I mentioned is much simpler than that model, but that's already was not analyzed. It's okay. I think there are some analytical results for maybe dense networks so far, but not fully analyzed yet.
Okay, thanks.
Can I make a few comments? So first, I'd like to thank Ganesh for very interesting observation. Ganesh has made so many links to various topics. In particular, he mentioned in short this links to the information theory when he said about Shannon entropy. And I would say that I think yes, it's very important. Information theory is a part of probability theory to some extent, to probabilities, and it's very important. And Shannon entropy is one of basics. And you can find, for example, this concept of Shannon entropy in in discussion information theory in Markov's textbook on probability theory. You may look at that, but it's very light touch of that. Another light touch was Ganesh mentioned Kinnman's coalescence. It's really beautiful. It's fantastic. Just imagine you assume how it's possible. You may consider the line, and on time zero, you start an independent Brownian motion from each point of that line. From each point of that line, it's possible. And when the when two Brownian motions meet, they couple, they stay. So what happens? You start from really uncountable state, all points, but immediately at any positive time, you get locally finite number of them. And they start to continue and so on. It's beautiful area. It's fantastically beautiful area. And there is a big, large number of research in that area, which is very close. To get a limit in this space is beautiful. Another topic I like, what Ganesh mentioned, it's coupling from the past. And I think the students, younger colleagues and students who attended my talk about my lectures about a year ago, they know that coupling of the past is very close to backward coupling. And there is a paper by Richard Tweedy and me, for example, 1998. I explained and said that coupling of the past is a particular case of backward coupling. So Ganesh has made so many links to various topics. I just mentioned 3 of them, but I think it's the course. It's nice to see how can he make links to so a huge variety of models and topics which are live in the modern probability theory. And Ganesh used only just simple tool, probabilistic tools. I appreciate this. Thank you.
Thank you, Sergey.
Thanks, Sergey. Ganesh, last time, 2 weeks ago, you sent us a list of exercises, and it was really cool. I think we enjoyed, at least I did.
Okay.
It will be for this.
Yeah, I can try to send some things. Last time I also sent one quite challenging problem. I don't know if I have that, but I have at least some easy problems this time, which I will send.
Okay. But this challenging problem, Marina, she solved it even before you sent it with like this, if I'm right.
Okay.
If before you send it with your comments, like not comments with steps.
With hints, yeah.
But, well, I just looked to the reference that you mentioned in your...
Svante Jansson's, yeah.
So it was unfair, but anyway. So it would be very nice if you will send us.
So who told, Marina, you or Svante Jansson?
For me, it was Marina.
Okay.
So, any more questions, comments?
Okay, I think we should thank Ganesh again. Thank you, Ganesh.
Thank you.
Okay.
See you next week.
Yeah, see you next week. Okay, I think our lecture is end.
It's next week, 29th of September, yeah, correct?
Yeah.
Okay, yeah, there was a break last week, but okay, now it's okay, it's clear. So,
you have a seminar at Friday, yeah?
Yeah.
Friday
Seminar on Friday at 17 hour by Novosibirsk time, UTC +7.
Okay. So thanks, Ganesh, again.
Thank you, Ganesh.
Yeah.
Ganesh, let's chat shortly now. Yeah, okay, you will call me. Oh, yeah, Ganesh.
Yeah, I'll call you now. Yeah.
Thank you.
Okay, see you. Bye-bye.
Bye.
Bye.
Thank you so much for the lecture.
Thank you.
Bye.
Bye.
Thank you. Bye.